All right, everybody. So where we left off is that we were working on the angular equation for a solution to the Schrodinger equation in 3 dimensions when we're in spherical coordinates and our potential is just dependent on the radial distance from the origin. So we came up with 2 solutions by separating our variables. For our phi solution, we came up with this exponential general solution. And because of our boundary conditions where we need it to be continuous, that limits us to m being an integer 0, positive or negative 1, positive or negative 2, and onward. Then our solution to the theta equation, which remember is our polar angle or angle from the z-axis downward towards the xy plane, is a little more complex, right? We need it to use the associated Legendre functions as part of our solution. Now, this is something you may have seen in a classical electrodynamics class. So there are equations for those polynomials. They're defined by the Rodriguez formula, which we can see here. There are usually tables of these in a book where you need to use them. So when we use that formula, L is limited to 0 or a positive integer, whereas M is going to be anything from negative L up to positive L. So there are 2L plus 1 possible values of M. There are other solutions to the Schrodinger equation, but they're unacceptable with the boundary conditions that we need to set. All right. So one of the other things we need to think about, since we want to think about our probability densities, is we need to think about what a volume element in our spherical coordinates would look like. So we already wrote in Cartesian that the volume element would just be dx, dy, dz. In spherical, our volume element looks like this. So we have an r squared, a sine theta, and then a dr, d phi, d theta. And that is just describing, if we're in our xyz, instead of having that little box, we have kind of a strangely shaped cube that is going a little further out in the r direction. And then in the theta direction, we need to do not just theta, but an r theta kind of, or an r d theta kind of description to get that length. And then in the phi direction, we need an r times sine theta d phi in that phi direction to describe that chord length. So that should be kind of review from using spherical coordinates elsewhere, but you might not have it memorized. Okay, so then our normalization condition, the reason we need this, our normalization condition in spherical then looks like this. Throw the word in there. So our normalization condition in any way is that we're going to look at our wave function, its magnitude squared, times our little bit of volume element. We're going to do an integral over all space where this exists, and that should be equal to 1. So here, our little bit of volume in spherical is that r squared sine theta dr d theta d phi. So that's really telling you to take a triple integral, right? And that should be equal to 1. Now, if I want to write this in terms of the general solution that we just came up with here, we've got whatever our radial equation is squared, r squared dr. That's one thing. And then we've got whatever our angular equation is, again, squared, sine theta, d theta, and then also d phi. And that should be equal to 1. So if this and this are equal to 1, you could actually normalize them separately. So let me grab another piece of paper. And we'll write that thought down. Could normalize our radial equation and our angular equation separately. Okay, so if we were to do that, we could just write down over all the radii where this exists. And remember, our r in spherical starts at 0, so there's no negative r values. Starts at 0, goes to infinity if we're in all space, or a limit different than infinity if we're limiting our wave function to just one space, a smaller space than all space. And that would be our normalization condition for our radial equation. Then again, if we are over all space, our phi goes a full circle in the xy plane, so it goes from 0 to 2 pi, and our theta goes from 0 to pi, so from the positive to the negative z-axis, and that would describe a full circle. So that order that I've put those in, the, whoops, I forgot my theta. The interior one is d theta, so that's this one. And the exterior thing is d phi, so that goes with this limit of integration. And normalizing that, that should be equal 1. And that still agrees with what we wrote here, that 1 times 1 would still equal 1, right? So we could normalize these separately and still reach our normalization condition. Okay, so what happens when we do that? Our normalized angular wave functions, they have a special name. They are what we call the spherical harmonics. And literally, the spherical harmonics could be harmonics. So there is an analog experiment that you can do where you use a spherical cavity and find the standing waves, sound waves, harmonics in that spherical cavity, and it will be a sound analog to what we're finding with our quantum equations here. Cat fur in my picture. All right. Working from home is great. So our spherical harmonics, we would have our angular equations, and I'm going to denote these with both the m and l quantum numbers that we already described. And remember, they're codependent. So the allowed values for m are dependent on what the allowed values for L are. So this is a function of both of our angles, so both theta and phi. I'm going to throw in this little epsilon and explain what it is here in a second. But we've got 2L plus 1, and we've got L minus the absolute value of m, and that's going to be a factorial. And then on the bottom, we have 4 pi L plus magnitude of m, again with a factorial. This is all under a square root sign. And then we've got an exponential function. And we've got our polynomial. So our polynomial, that's a function, sorry, my handwriting just went off the wall there. That's a function of cosine of theta. All right, so that epsilon that's in the front, that is just going to be -1 to the m, right? So if it's -1 to the m, and again, this is for m greater than or equal to 0, then that is letting us know whether we have a negative sign or not in front of here, right? And then What about for our negative values of m? Well, it's just going to be 1 for our negative values of m. All right, so that lets us know that our spherical harmonics are orthogonal. And we can actually name these quantum numbers that we're using here L, because it has to do with the things on the z-axis, our theta equation. Our L is the azimuthal, right? Say that 5 times fast, quantum number. And the M is our magnetic quantum number. So we will define those two things and come back to them again. All right, that seems like a good place to take a break. I'm going to pick up with our radial equation next time.